The relationship between the change in free energy and Q, the reaction quotient, is very important to understand. The change in free energy, or delta G, is the instantaneous difference in free energy between the reactants and the products. Q is our reaction quotient. It tells us where we are in the reaction, and remember, it has the same form as the equilibrium constant, K. Delta G0 is the standard change in free energy, so the change in free energy under standard conditions. R is the gas constant, and T is the temperature in Kelvin. Remember, when delta G is less than 0, so when delta G is negative, the reaction is spontaneous in the forward direction. When delta G is greater than 0, so when delta G is positive, the reaction is non-spontaneous in the forward direction. And when delta G is equal to 0, the reaction is at equilibrium. Let's apply this equation to an example. So here we're trying to synthesize ammonia. So our goal is to calculate the change in free energy. So we're trying to find delta G for the following reaction at 25 degrees C, given the following set of partial pressures. So nitrogen gas plus hydrogen gas gives us ammonia gas. And at 25 degrees C, the standard change in free energy, delta G0, is equal to negative 33.0 kilojoules. And remember, for gases, it's easier to measure pressures than it is to measure concentrations. So at this instant in time, the partial pressures for all of these gases are 1 atmosphere. So 1 atmosphere for nitrogen, 1 atmosphere for hydrogen, 1 atmosphere for ammonia. So at this instant in time, calculate the change in free energy. So we're trying to find delta G, so let's write down our equation. Delta G is equal to delta G0 plus RT natural log of Q. So we need to find Q. We need to find our reaction quotient. Remember, it has the same form as the equilibrium constant. For our equilibrium constant, we had the concentration of products over the concentration of reactants, and we raised the concentration to the power of the coefficient. But here we're dealing with partial pressures, right, instead of concentration. So I'm going to write Q sub P here to remind ourselves that we're working with partial pressures. So that would be the partial pressure of our product, so the partial pressure of ammonia, raised to the power of the coefficient, so raised to the second power, over the partial pressure of nitrogen, so the partial pressure of nitrogen, raised to the power of the coefficient. In our balanced equation here, the coefficient is a 1, so this is raised to the first power, times the partial pressure of hydrogen, raised to the power of the coefficient, which is 3, so raised to the third power. So everything is at 1 atmosphere at this moment in time. So this would be 1.0 squared over 1.0 to the first power times 1.0 to the third power. And all that, of course, is equal to 1. So at this moment in time, our reaction quotient Q is equal to 1. So to solve for the change in free energy, so to find delta G, we take Q and we plug it into our equation. So what is the natural log of 1? That, of course, is equal to 0. So this is equal to 0, and we find that the change in free energy, delta G, is equal to the standard change in free energy, delta G0, which at this temperature is equal to negative 33.0 kilojoules. So the change in free energy, delta G, is equal to negative 33.0 kilojoules. All right, let's talk about a few things here. First, we got a negative value for delta G. We got negative 33.0. So our reaction is spontaneous in the forward direction. So we're going to make more of our products. We're going to make more ammonia here since delta G is negative. It's our driving force to make more of our products. Notice that delta G, in this example, delta G is equal to delta G0, and that makes perfect sense because delta G0 is the standard change in free energy. It's the change in free energy under standard conditions, which is what we have here. We're under standard conditions. Everything is at 1 atmosphere, so that makes sense. And finally, you could write, if you wanted to, you could write kilojoules per mole of reaction, indicating for this reaction, how it's written right here, that is the change in free energy. So when 1 mole of nitrogen combines with 3 moles of hydrogen to give us 2 moles of ammonia, delta G, the change in free energy for that reaction, is negative 33.0 kilojoules. Now let's get a new set of partial pressure. So now let's say all of the gases have a partial pressure of 4.0 atmospheres. And when all of the gases have that partial pressure, what is the change in free energy at that moment for our reaction at 25 degrees C? So we're trying to find the change in free energy. We're trying to find delta G, and we know delta G is equal to delta G0 plus RT natural log of Q. So we need to find Q, the reaction quotient. So this is QP, and from the previous example, we know how to find Q. So I'll go through this a little bit faster. This would be 4.0 to the second power, so 4.0 squared, over 4.0 to the first power, so 4.0 to the first, times 4.0 to the third, so 4.0 to the third. 4.0 squared is 16 over 4 times, let's see, 4 cubed is 64. So what is Q equal to? We get out the calculator. 16 divided by 4 times 64 is equal to 0.0625. So at that moment, the reaction quotient is equal to 0.0625 at the moment when all of our partial pressures are 4 atmospheres. So this is our reaction quotient. We're going to plug this into our equation, and we're going to solve for delta G. So delta G is equal to delta G0, the standard change in free energy. At 25 degrees C, delta G0 is negative 33 kilojoules. So we have negative 33.0 kilojoules. We need to make that joules. So I'm going to say times 10 to the third joules. Plus, R is the gas constant. So that's 8.314. So 8.314, and that's joules over mole times K. Since the gas constant is in joules per mole, we need to make delta G0 in joules per mole too. Next we have the temperature. So the temperature of our reaction is 25 degrees C. That needs to be in Kelvin. So 25 degrees C is 298 Kelvin. So we write in here 298 Kelvin. So Kelvin would cancel out here. And then we're going to multiply that by the natural log of Q. The natural log where Q is equal to 0.0625. 0.0625. Let's do the math. So let's start with the natural log of 0.0625. So the natural log of 0.0625 is equal to that value, which we need to multiply by 298 and multiply by 8.314. We're going to add that to delta G0. So plus negative 33.0 times 10 to the third. And that should give us our change in free energy, which is equal to negative 39.9 kilojoules per mole. So I'll round that. So delta G is equal to negative 39.9 kilojoules per mole. So it's just easier to think in kilojoules. And remember, this is moles of our reaction. So for this specific reaction, where 1 mole of nitrogen combines with 3 moles of hydrogen to give us 2 moles of ammonia. So how it's written, delta G for the reaction, how it's written is equal to negative 39.9 kilojoules. So delta G is negative, and so we know our reaction is spontaneous in the forward direction. So the reaction is spontaneous in the forward direction, which means we're going to make more of our products. Let's think about how far away we are from equilibrium. All right, so Q, our reaction quotient, is 0.0625. For this reaction at 25 degrees C, the equilibrium constant, which would be Kp, is equal to 6.1 times 10 to the fifth. Our value for the reaction quotient was 0.0625. That's much, much smaller. That's much smaller than the equilibrium constant. So Q is much smaller than K. So we know we have too many reactants and too few products. We have a driving force. Delta G is negative. We have a driving force to make more of our products. So the reaction moves forward to make more products here. So we know that by just looking at the sign for delta G, which we know is spontaneous. We also know that from comparing the reaction quotient Q to K. So because Q is not equal to K, we're not at equilibrium here. We are away from equilibrium, and we have a spontaneous reaction. All right, so we're going to make more of our products. So the reaction proceeds to the right. We make more of, overall, I should say. We make more of our products, and we lose some of our reactants. What happens to Q? So as the reaction progresses, we make more of our products, so the numerator should increase. We lose some of our reactants, so the reactants should decrease. And so if you think about that, an increase in the numerator, a decrease in the denominator, that means that as the reaction progresses, as the reaction moves to the right to make more products, Q should increase. So as Q increases, what happens to delta G? So let's think about that next. So if we get an increase in Q, what happens to the change in free energy? Well, let's just make up a number here. Let's say that Q is now equal to 100. So we're at a different moment in time. Here, Q is equal to 0.0625. Let's increase that to Q is equal to 100. So if we increase Q, what happens to delta G? Let's just plug the numbers into the equation and let's see for ourselves. Delta G is equal to negative 33.0 times 10 to the third. That's joules per mole. Actually, let's just leave out units here to make it a little bit, to give us a little bit more room. All right, plus, so that's delta G0, plus 8.314, our gas constant, times our temperature. We're still at 298 K. So the only difference now is we're substituting 100 in for Q. So we've increased the value for Q. What happens to delta G? Let's do the math. So we need to find the natural log of 100, and we multiply that by 298, and we multiply that by 8.314, and then we add that to delta G0. Delta G0 is negative 33.0 times 10 to the third. So we get, in kilojoules per mole, that would be negative 21.6 kilojoules per mole. So delta G is equal to negative 21.6 kilojoules per mole of reaction. So we increased Q. Right, we increased Q. What happened to delta G? We went from a delta G of negative 39.9 to a delta G of negative 21.6. So we're getting closer to 0 as the reaction proceeds to the right. We're still spontaneous. We still have a negative value for delta G. So we still have a driving force to make more products. Q is still less than K, right? Q is 100 and K is 6.1 times 10 to the fifth. So we're still going to go to the right and make more products. Our reaction is still spontaneous. What happens at equilibrium? All right, so what happens at equilibrium? We know already that delta G should be equal to 0 at equilibrium. So at equilibrium, delta G should be equal to 0. And Q should be equal to K. The reaction quotient is equal to the equilibrium constant. Let's plug that into our equation and see if that's true. So we have delta G is equal to delta G0, negative 33.0 times 10 to the third, plus the gas constant is 8.314. Our temperature is still 298. But instead of writing Q, we're going to plug in K. We're going to plug in the equilibrium constant, which I already gave to you up here, is 6.1 times 10 to the fifth. So now we're doing the natural log of K. So we plug in the natural log of K, which is 6.1 times 10 to the fifth. And let's see what happens to delta G. So now we're going to find the natural log of 6.1 times 10 to the fifth. And we need to multiply that by 298 and then multiply that by 8.314. So we get positive 33 kilojoules, right? So positive 33 kilojoules, or 33.0 times 10 to the third. So notice what happens, right? Over here we have delta G0 is negative 33.0 times 10 to the third. And all of this on the right gives us positive 33.0 times 10 to the third. So that, of course, is equal to 0. So the change in free energy, right, is now 0. And we are at equilibrium, right? Q is equal to K. We plugged it into our equation, and we found that delta G is indeed equal to 0. So there's no more driving force to make more of our products, right? There's no more driving force to make more of our products because we are at equilibrium. The free energies of the reactants and the products are equal.